Hi guys, we'll get started in just a second.
Sounds good. Hello.
Hello,
Hello.
how's it going?
Howdy.
Hey, thank you guys again for the eggnog. It was super good. Knocked it out
Glad
of
to
the
hear
park.
it.
Very nice.
Yeah, it was delicious.
I've heard good things so far from pretty much everyone, so I'm pretty happy with that.
That's awesome. The bottles were cool too.
I did like those. I did like those. Because I was like trying to figure out I was like jar, but then I saw those and I was like, no, that's so much better than a jar.
It is. All right. Let me just get this. All right, guys. So I'm just gonna go right in with the practice questions. So lots of review. I went through all the questions earlier today and really hoping that there's not anything that's going to be new material. I think we actually did a pretty good job going through it. I think we probably, if I look back at the classes, we probably spent more time than needed on like lensometry and progressives. Um, but I think those things, like if you do go on to do like the practical exam, those things will really serve you well, like at that stage. So, but otherwise, what I'm going to do is just do a whiteboard as usual and keep going through questions. There was one that I ended last time on, and I just kind of was thrown by that. So I wanted to start with that one. But I'm just going to go ahead with a whiteboard and put that question up again real quick. If I can get myself going here. Let me see if I can just copy and paste. That would be so much easier. No. Okay, I gotta snip them apparently. All right, so the question, it wasn't the last question that we had discussed in the last meeting, but it was one that had come up. Let me just move this up a little bit. So it talked about using a lens clock to determine the powers of a lens. So basically what you need to do is, we'll go over this. There are a couple questions on this that we're going to go into in a second. But you need to use a lens clock at times, or theoretically, you would need to use a lens clock at times to determine the power of a lens. So you would read both the front surface of a lens as well as the back surface of a lens. And sometimes on the back surface, you'll find two different powers. Okay, so on the front surface, modern lenses are always just going to be completely spherical. We don't have astigmatism ground into the front of a spectacle lens anymore. So you only need to, measure one axis on the front of a lens, but on the back, you want to measure the axes 90 degrees apart from each other. But basically, what this question asks is, when using a lens clock, to measure the distance portion power of a one-piece multifocal, position the pins. So it's basically saying, where would you position the pins in a bifocal, right? So one piece multifocal in this sense means like a fused bifocal lens. So the little segment is fused onto the front of the lens. And when you think through this, basically it really only makes sense to measure it be horizontally above the segment line, right? Because if you think about it, just to not spend too much time on this, because this is a little bit honestly of a random question, but if you have a bifocal blank, it's going to look something like that, right? And if you imagine the pins of a lens clock, you're going to want those three pins to be like there, right? It wouldn't make sense to put one of those pins like if you were to go vertically, it wouldn't make sense to put one of them on the segment, because then one of those little legs is going to be raised up and you're not going to get an accurate base curve measurement. So basically, long story short, you would want to be going across horizontally and you'd want to be going above the segment line. Okay, so B is, I should probably type that in there just so that if you're ever looking at this again, you could see that. But basically, B is the answer in that case. Okay, so let me move on a little farther. I think we got to question 82 last time, which had to do with polycarbonate and how reflective it was. So I won't go to that one again. The next question goes into a little bit of anatomy. And I know that this is definitely a question that our tech lead, Kerry, has asked of her techs many times. So I will put this one in. But it asks about the layers of the cornea, and would go back to our first class that we had done. Well, I guess the first kind of real class. So I'm just gonna put in the layers one more time. But this is definitely something that very well could be on the test. So just, learning the layers, knowing basically, kind of you could do it maybe as like an acronym like EBSDE, might help you kind of remember what the order of the layers are. But basically, it is epithelium, Bowman's, stroma, descemet, and endothelium. Okay, so that's just a little picture of what that would be. And I'll move this down and just quickly type in A so that let's try to see that a little better. So that's the answer there. But definitely something that could very well appear. All right, and then just to keep on going here with more questions. And I'm just going in order from the questions that I had had shared with you guys. I think has been a couple weeks, but it's just the same document basically. One notable advantage to the executive style bifocal lens is A, light in weight, B, virtually invisible segment line, C, produces a thinner lens, and D, wider region for near vision. So one of the things I would always recommend for you guys, while I'm just putting in a picture here again to show you, is you want to do elimination, right? Like, so part of being, as we've talked about before, a good test taker is to not just know all of the answers. I mean, obviously that would be ideal, but it's also to be good at eliminating what it's not going to be. So if you're thinking bifocal, virtually invisible segment line would definitely, not make sense in this case. So you could really kind of, reduce that or take that one right out. The other one's light in weight, produces a thinner lens. Again, kind of questionable with a bifocal, especially if you know what an executive bifocal looks like. Those don't really make any sense. But anyway, the answer is D, wider region for near vision. And just a quick reminder of what an executive bifocal looks like is right over here, also called the Franklin bifocal. So sometimes on the test, they might try to trick you and, not call it executive, but call it Franklin. So just keep an eye out. It's always good to have in the back of your mind what some of the other names might be. One of the things that it does say is it's very thick and heavy. So that is a good eliminator for producing a thinner lens and being light in weight. But executive bifocals, that you can still get them, I believe, at some labs. Definitely not anything common at this point. And I've never been asked for one, but if you ever had a patient that really wanted one, definitely would not be a vision plan option. But I'm sure you could get one. So All right, let's keep moving. I'm going to try to move relatively quickly today because I do have a lot. If you've looked at this document, it's pretty extensive. So I have a lot of questions to go through. All right. Next one. So here we get to our decentration and starting to kind of look at base in, out, up, down prism. Okay, so definitely something we went over a good bit. I think it was video 5 or class 5, might have been 4. So if you need, if you want to refer back to that class will go over that a lot. But the question is, if a +7 diopter lens is decentered 32 millimeters, but the patient's monocular PD is actually 34, the patient would be looking through which direction of prism? Okay, so the first thing that you want to remember with these guys is you want to think about what the shape of the lens is going to be. Okay, so if you know that it is a +7, you're going to just remember that a plus shaped lens is either going to look like that or like this. Okay, so depending on which type of centration we're talking about, vertical centration, you're going to be thinking about this one. Horizontal centration, you're going to be thinking about this one. Okay, so they don't actually really specify whether it's vertical or horizontal here, but the fact that they're talking about a PD tells us that it's going to be the eyes being in or out, which should be like, okay, cool, it's horizontal, right? So let's go ahead and just draw this out. I find this to be the easiest way to visualize this. You may get really good and just kind of, not necessarily need to draw it out. But basically, we have the person here with their eyes and their nose, and let me just draw the lenses here. So ideally, what I like to do here is draw where the lens should be going, right? So if the patient was correctly centered with the lenses. We have on the green line where the center pupil is, and that would be their PD is actually 34, right? So basically, what we know though is that it was decentered some and it was done to 32. Okay, I actually drew both eyes, and I totally didn't need to. Now that I think about it, we're really only working with one eye because obviously this is not a binocular PD here. This, that would be really, really tiny. But so it's just one eye. So I really didn't need to do both, but we have it anyway. Okay. And so then what we would do is if we had the lenses placed correctly, if they were centered, I would make the base of this prism right over this green line. But in fact, we know that they are actually decentered to 32. So that means when I draw the base of the prism, I'm going to draw it so that the base is in, and it doesn't matter for our intent and purposes right now how many millimeters in it is, but we know that it's supposed to be narrower because it's 32, not say 36 or 38, right? It's going to be closer to the nose. So in this case, what we just need to do is we need to say, okay, what's the direction of the base? So the base is here. We're focused on this triangle or this prism here. So in this case, the base is in, right? It's toward the nose. It's not going out towards the temples. So this would be base in prism. Okay, so this one is not asking us, how much base in prism is induced in this case. We could figure that out with Prentice's rule, and there are a couple of problems with that in a few. But that's just a quick rundown of how you would do that. Obviously, my drawing is more involved than it needs to be. You could do this fairly quickly on a scrap piece of paper during the test. Okay, but that is most definitely something that is going to be on the test, what the direction of the base would be. So that's definitely something that you would want to get pretty comfortable with. Okay. So now we have a question for nominal lens formula. So they say if a lens has a plus 60 front base curve and a minus 8 back surface curve, what would be the nominal power? Okay, so basically what they're saying here, nominal power is just a way of saying what is going to be the power of the lens. So I'm just going to quickly remind you guys what the nominal lens formula is by putting in um, what that is from our readings. So nominal power formula is the front curve plus the back curve equals the total power of the lens. I think we also learned this as F1 plus F2 equals uh, total power. So that's just another thing to remember there. Okay, so they're giving you a couple options. Obviously, it's going to be either 1450 or 150. But we have to just make sure we get the signs right in this case. So this is where it can get a little confusing, is how do you make sure your signs are correct. So I'm trying to keep that on the page there, but let's go ahead and just take a second to draw this out. So if we had, say the two, let's say the one on the left is F1 and this one is F2. I should also say that you want to take note in this particular case that this is a spherical lens, okay? So there's only one front surface curve, which makes sense, right? Because there's only going to be one curve on the front. But the really important part here is that there's only one back surface curve. If the lens had astigmatism, it would have two back surface curves. And I know there's a question in this that we'll go through with that example. So if you can't quite remember what that's going to be like, we'll go ahead and do that. But basically, if the front was, I'm kind of writing, an optical cross, and I've got to make sure my signs are here. If the front is 650 both at the 90 meridian and the 180 meridian, it's going to be 650. If our readings of the lens clock at the back are on an optical cross, we would be -8 and -8. Okay, so that's just I wouldn't say you have to draw this out, especially if it's spherical, but this is what it would look like, and this would be helpful if you had cylinder involved. But basically what you're going to do at this point, make this a little tiny bit darker, is you're going to be like, okay, plus 650. We're doing the nominal lens power now. So the F1 goes here, plus -8 is going to equal our total power. Okay, so our signs here, we're going to, the negative, is going to be kind of trumped by this. So you're going to take out this, but basically we're combining the -8 and the plus 650. So your power, oops, I forgot my one here, is going to be a -150. Okay, so traditional algebraic math in this case, dealing with positive and negative numbers. And so if we go back up here, it is going to be C, which is the -150. Okay, so pretty straightforward, I think there. Obviously, they're trying to confuse you with the -1450, and that does get nerve-wracking because you're like, wait, do I know how to do this? But if you just follow, oh, sorry, I didn't mean to do plus here. That makes no sense. Sorry about that. I pressed shift when I shouldn't have. Equals total power, sorry. But basically, if you just follow the math, that makes sense, right? I think they're trying to trick you into thinking that you have to add a plus 650 into +8, which obviously would be the 1450. Okay, so that one goes like that. And then my next one, actually, I'm glad I have this in order here, is going to be with astigmatism. So let's just kind of go through the same thing, but using an astigmatism example. So let me just put in that question real quick. Okay, so again, using a Geneva lens clock, you determine the following lens information. The front surface is a plus 850. Okay, so let's go ahead and draw that out. I'm sorry, 825. Oh, where did I get that? 825. Okay, now we know that the front surface is going to be spherical, so at both my 90 and 180, I am going to have those. And then for the other surface, here we go, we have one of them reading at a minus 650 and the other one at a minus 475. Okay, so that means when you took those three prongs of the lens clock and you read the lens, you did not get a spherical reading. It wasn't 650 in both meridians. The farthest difference between those two that you could get power-wise was getting one to, the 650 mark and one to the 475. Okay, so basically now we're going to do the same thing, that same formula, the front curve plus the back curve, or the F1 plus F2. It gets a little bit more complicated just because we then have to put it back into an optical cross. So let me go ahead and do that. It might be a little easier for me to just type this out so it's a little bit neater. But we then have, I should put the positive sign in here, plus 825. And then we're going to combine that with a minus 650. Okay, so if we do that math out, we are going to get a plus 175. Okay, and then let me do the next one here. We're also going to put together a plus 825 and a minus 475. And if we put those two together, we're going to get a plus 350. Let me make those a tiny bit bigger just so they're a little bit more visible. Okay, so in this case, we have to do a little bit more work because of the different powers, but we now have a plus 175 and a plus 350. Okay, so what this is here is this is a new optical cross. And to get to the actual prescription, I mean, this is like not how we write things out, but this would be another way to, kind of write out prescriptions. It just is a lot more numbers than the way that we kind of do it. So basically what you're going to need to do in order to get to the answer here, because the answer is actually a prescription, right? They're not asking for all of it, they're not asking for like the two different surface powers, right? Or the two different, cap powers like of the lens. They're asking for the actual script. So that means that we have to put it back into an optical cross. Okay, so because we are in the optometry world, we are going to put the most plus power at the top. So that's going to be the 350 at the top of the optical cross. And then we're going to move more minus. So we're going to put our plus 175 here. And when we do out this math, that difference between them, because remember, we're always looking at the difference between, and we're always going to go in that minus direction. The difference between those, I would take out my calculator for this normally, but I have this already figured out, is minus 175. Okay, so that means that if we were to write out this Rx after optical crossing it, it would be plus 350 minus 175. We don't know what the axis is, right? They never really gave us that information. But if we did know what, maybe this is, maybe this is 90, right? They didn't really tell us that in the question, where they took these measurements. But basically what this would say is this is the actual prescription, right? So just long story short, these numbers basically mean the same thing as this prescription. This is just how we notate that in optometry, right? So if I go back to the question here, it's going to be A. It's going to be the plus 350 minus 175. Okay, so there were quite a few steps to that one. I don't think that that's going to be, you definitely want to know how to do that. I don't think that that's going to be a huge part of the test, but I think that there is a chance that that could be on there. So you definitely, want to know your nominal lens formula. And then, once you do get your results, you want to know how to put that into a prescription, right? So a lot of this has gone over. I believe it's in video 5. We did a lot of stuff related kind of to these things in that video. So I would, if you want to see more about this, I would take a look at that video again too, before going into the test. All right, so let's keep going along here. All right, so this is something that always throws me. It's really kind of just memorizing it. But let me tell you, which is, I think, a good thing, because if you just memorize it, then you're going to know it. But the question is, if a plus powered lens is moved farther from the eye, it will effectively become more blank to the wearer. Okay, so the options are plus, minus, or cylindrical. Okay, need more information. So the thing that you need to remember is that when things are moved, and this is like true of both plus and minus lenses, okay? When they are moved farther from the eye, they gain more perceived, meaning you would see more plus power. Okay, so I think I had drawn this out in another video, but basically, the farther something is moved from the eye, the more plus. Okay, and then if it was going, back towards the eye, um, you know, then it would gain, more perceived minus power. But I think the thing that really, and I'll just type it out real quick because I really think the thing to remember is the farther from the eye, the more perceived plus power. And perceived is important here because it's like, what does the patient actually register? What are they seeing, right? So, long story short, if something is moved away from the eye, to maintain the same power, it would need to get more minus. It would need to have more minus power added to it as it got farther from the eye to counteract all that plus power that's happening because it's being pulled away. Okay. So we'll go through one. The following question talks about this as well. But that's something that I really would just try to commit to memory is that if a lens is moved farther away from the eye, it gains more perceived plus power. I do have a little helpful picture that I'll put in here that would be good for like studying or remembering too. This really just goes through, you know, like it talks about it. It's the same concept, just said in a different way. I like this kind of idea up here where you just say it one way. But this talks about, okay, what if it's a minus lens? What if it's a plus lens? So if you really want to be very specific about it, you could, memorize all 4 of these. But you could just memorize this one and then just think to yourself, okay, if it's farther away from the patient, it's just going to need more minus to be the same RX. Okay. If it's closer to the patient, it's going to need more plus to be the same RX, right? So anyway, that long-winded thing basically means that it would be A in this case, right? So I will put that there for the answer. Okay. So let's go through this in terms of another type of question that relates to the exact same thing. I do have to say this question is a little bit weird. Sometimes these practice tests are not the best edited. So by the way, I do have a lot more practice questions that, I have the answers to. So I'm going to share you guys those as well, for, studying and stuff. But these ones in particular I found were a little funny, but and I'll tell you why in a second. But basically, this one says a patient with the RX of plus 225 OU and with an exam vertex of 12 millimeters visits you for their glasses. You find that when you fit the new frame, the lenses will sit 16 millimeters from the eye. What changes would you make in the lenses to be ordered? Okay. So basically, this is kind of the same deal. In this particular case, the patient was behind the phoropter. When they got their refraction, it was only 12 millimeters, right? Before the lens. But then when the glasses were actually fit, they got an additional 2 millimeters farther away from the patient. Okay. So what does that mean? Okay, well, this is a plus lens. So what's going to happen? The farther away, the more perceived plus power. So in order to maintain that same RX of plus 225, we're going to have to add a little bit of minus to that power. Okay. So, if we could figure this out with our vertexing formula, but it's a fairly high RX. Maybe they're going to get like a plus 12, right? Or maybe a plus 1175 or something, right? But we don't have to figure that out for this particular question. So the answers are, or the suggestions are, does it gain more plus power, more minus power, or less minus power and less plus power? So if you look at that for a second, you realize that both of these are like the same thing because more minus power is the same as less plus power, and more plus power is the same as less minus power. So it's basically they're only giving you two options. But in this case, what's going to happen? What changes should you make in the lenses to be ordered? They need to be more minus or they need to be less plus. So in this case, the answer is both B and D for this question, right? So, what else? Let's see. Okay, so now we have our vertexing question coming up next. So that's a good thing where we can use our vertexing formula. So, whoops, hold on. I scrolled down too much here. Let me put in that question, kind of a similar high power. The reason, one other thing just for practicality is the reason that these questions about vertexing are high power lens questions is because vertexing really only makes a huge difference at higher power lenses, right? So you're not going to be super worried about this. If you fit contacts, you know this. It's not something that you're really even considering much until, the 4 diopter mark, right? But okay, so this question says a plus 12 lens is prescribed at a vertex of 13 millimeters. The optician fits the finished glasses at 9 millimeters. So what is the power? What is the power of that lens at the fitting position? Okay, so basically in this case, the lens was in the phoropter was farther away. Now the glasses are sitting really close to the patient's eye at 9 millimeters. So we have to kind of figure out how that prescription has changed. So let's go ahead and do that. So one thing, I'm basically what I'm going to do is I'm going to give you the formula, but you could also, kind of think about this a little bit too, just by what we know from up here, because we know that if that plus lens was moved away from them, it would gain in plus power. But if it's moved closer to the eye, it's basically, going to be reduced in plus power. So most likely, we're going to be, not at the 1225 mark. We're going to be, lesser than that, right? It wouldn't make sense for it to suddenly become, a higher powered plus lens. Okay. But what we're going to do is we're going to use our vertexing formula, which is this. Let me just put that in. So this is the power of the lens squared divided by 1,000 times the millimeters of change in the distance. Okay, so basically they make this relatively easy for us because we would do 12 squared. Okay, so 12 squared is 144. Okay, and then just make that a little bit bigger. And then what we would then do is go ahead and if we divide, sorry, and then 144 divided by 1000, and then I actually don't have my phone on me, but I did the math out already. But we would do 144 divided by 1000. Okay, so that's, the first part of this formula. Okay, and then what we would do is multiply that by the amount of millimeters of change. So the millimeters of change in this case that we need to, you might be like, okay, how do we figure that out? Well, it's started at 13 millimeters. Now we're at 9 millimeters. So that's going to be 4 millimeters of change. So let me get back in here. So times 4 millimeters. So when you do that math out, that is going to come out to 0.576. So the plus lenses at this point are moving closer to the eye. So they are going to be basically, we know that they're going to decrease in power. But what we would then do is say, okay, cool. We started with our plus 12 lens. We're going to subtract that 0.576 to be very specific. And that is going to be very close to the prescription of a plus 1150. Okay, so they obviously, just kind of rounded this, obviously, but that would mean that our end result here using our vertexing formula would be a plus 1150. So that would be B. Okay, just to write that in there. That one's tricky. Normally, what I would say to do and what I think would actually be on the test is I think they'd want to just know that you understand what happens to lenses when they move away from the eye and come closer to the eye. So I think this is good to know, but I wouldn't make this like my top formula to remember, right? Like nominal lens formula is way more important. Prentice's rule, which we'll go over soon, is also way more important than this. Okay. I think on the actual test, they wouldn't give you this many possibilities because they basically gave you two possibilities, which it could be the plus 1150 and the plus 1050. I think they would probably make it a little bit easier so that you could just kind of like infer the answer by knowing, okay, I understand this stuff gets more plus when it's farther away and more, minus when it's closer. So, anyway, what else is this? Okay, so this one, you may get a question about this. Little bit of a pain in the neck because I feel like you really just have to memorize this. Sometimes, like, I hate, like, oh, you just have to memorize these. Because in some ways it's great because you would know it, but in other ways it's like, ugh, how do you know what to memorize? But this one is about base curve. So it says, what base curve is recommended using the single vision RX below? Gives you the prescription, and then it gives you the options of Plano +6, +325, +875. Okay, so remember that the base curve is basically just the curvature at the front of the lens. Okay, so it's whatever this curvature is, and there are ideal base curves for all powers of lenses. And I'm just going to remind you of this chart. Again, I do think it is a little bit of a bummer because you kind of just have to know this one. But I think that they would probably give you something that's going to be relatively in the middle of this chart. But basically, in this case, what we would do is we would look for the 425 and the 350. The sill, the sill is there, but it's fairly minimal. And you'd kind of figure out, okay, where does that fit? So it's the 425 and the 350 minus, of course, would fit here. So what they're saying in this case is they're like, all right, the ideal base curve for this power would be a 4. Okay, so the problem, of course, with that is that that doesn't really coincide perfectly with any of the options that are here. I do think there's a little bit of wiggle room on this chart. I don't think that every optical, company, or there's not just one single chart. There's a little bit of, different stuff that happens on these charts, but you basically want to be like, okay, what is it closest to? And obviously the +4 is going to be closest to the 325 in this case, right? So jumping all the way up to a +6, they would have to be much less, minus, almost to plus. So it's really the 4 that makes sense in this case. So we're going to go with what's closest to the 4, which is going to be C in this case here, for that answer. And again, just for studying on this one, I would focus really just like maybe on these areas. I would really just try to know like these middle ones, because I think it's the chances of you getting asked about the higher end powers, I don't think that's a big chance. Okay. So we now move into the cylinder power and axis. So we did talk about this. It has been a bit since we talked about this one. This was, I looked back to see because I was like, oh no, did we go over this? But we did, and it was back in September. So it has been a little bit since we talked about this. But let's remind ourselves here. I feel like I have other questions about this, so I apologize if we end up coming back to this a little bit disjointedly. Sorry, I think I do have more later, so we'll kind of gloss over those a little bit when we come to them. But for the prescription of -225, -225 at 100, in which axis is all of the cylinder power present? Okay. So if you guys remember, and I'm just gonna quickly scroll down here because I did make a little nice note of this somewhere in here. And I think it would help us. Hmm. Sorry, guys. Where did I put this? Okay. I found it. Okay. So the things to remember about cyl power. We did talk quite a bit about cylinder power, but the things to remember are on the cylinder's axis, there is no power. Okay. Because remember the way a cylinder works, it's at full power in one meridian and at 0 power in another meridian. Okay. So on the cylinder's axis, there is no power. So if we are at 100, there is no cylinder power there, just sphere power. Okay. 90 degrees away from the cylinder's axis is full power. So that whole 225 in this case, and 45 degrees away from the axis, it's half power. Okay, so that is a very, very important concept. You will definitely get some questions about this. Okay, so this is pretty easy in this case. Basically, what we want to do is we want to change that axis 90 degrees, right? So if we change this, if we subtract 90, we can't add 90 to this because we would then be at axis 190, which doesn't exist. Our axes only go to 180, right? So we're going to subtract 90 in this case, and we're going to end up at 10. Okay, so that basically means that in this particular case, it's going to be B. Okay, so pretty straightforward on that one, but definitely you want to be remembering how the cylinder works. And when you see that cylinder number written, that's no power. Okay. All right. So let's do a couple or one. I think I just have one more of those. And I'm going to do that one next just since we're on that topic. So let's go ahead with that one. All right, so this question says, the given Rx of -2, -4 at 110, what is the power at the axis 80? Okay, so we need to remember this above about where the power is likely to fall. So the confusing thing about this is it's 30 degrees away. Okay, so because if we subtracted 80 from 110, it's going to be 30 degrees. So that's a little weird because that doesn't really fall into our schema of 0 degrees, 45 degrees, and 90 degrees, right? But we do know that it would be half power at 45 degrees away from the 110, right? So basically, let me just grab my calculator here so I'm not making a mistake, but 110 minus, oops, 110 minus the 45, right, would be at 65 degrees, would be basically at half power. Okay, so we're kind of between that marker, right? So we could say, okay, if we're at a quarter power, I'm just going to write this down, at 65 degrees, right? So a quarter power, I'm sorry, I shouldn't have written that. A half power, I should say, half power is at 65 degrees. Okay. So basically what I did was I was like, all right, let's figure out, because we have this kind of weird thing of 30 degrees, I'm like, all right, let's figure out where we would know that it was half power. So I'm like, okay, we know that it's half power, 45 degrees away from 110. So I said, okay, 110 minus 45 is going to be 65 degrees. So we know that at 65 degrees, we would be at about half power. If we think, okay, what is about half of 65? Well, that's going to be 30 degrees. Okay, so or about 30 degrees, I guess it would be 32 and a half degrees, right? So from that, I'm going to say, all right, we're going to be at a quarter power at 32 degrees. So if I look, so I kind of deduce that, to figure that out. And then I'm like, okay, what is the actual sill power? The actual sill power is a -4. That actually works out really well for a quarter power, right? Because 1/4 or 1/4 of 4 is going to be 1 diopter. Okay, so if we say 1 diopter is going to be the power. I'll put this next to here so that we know that it's referring to this, but a quarter power is at 32 degrees, and that's going to be 1 cell power, right? So if we were to figure out, okay, what is that power, we would be like, this Rx would now be -2 minus 1 at 32 or 30, right? So if we have a -2 and a -1, and I should make this a -1 so it's not confusing, but if we're combining this one with this one, we're going to get a -3 for our power. Okay, so that basically would tell us that at that particular axis, we would have a power. So the answer is going to be A. We would have a power of -3. Okay, so again, that's a fairly complicated one. I'm trying to give you questions that are like fairly involved. I don't want to scare you, but I also want to give you like an example of it. So my guess is that you're not going to be asked randomly 30 degrees. I think the questions you're going to be asked are like, what is it on the axis? What is it 45 degrees away? What is it 90 degrees away? So getting to 30 is kind of odd. But you can kind of, make an educated guess by going through these steps. So hopefully that is helpful. We did a lot of that in or we talked, a good bit about that in our meetings. I think it was like 4 or 5. So if you wanted to go back to that, you could also do that. So let me go back in my questions so that we go back to what we were up to here. Let me just find it. Sorry. Okay. Here I am. All right. So continuing on. I do have one more about that. Okay. Actually, no, I don't. That was it. This one's about reading power. Okay. So the next one, reading power. It's funny because we just kind of talked about this in the optical training. But this question talks about making a reading prescription. What would the reading power be for the following RX? So pretty simple here. Plus 175 minus 125 at axis 10 with an add of 225. Okay, so we know that when we make a single vision reading prescription, we are going to be combining just the sphere power with the add power. So pretty darn easy. We are going to be combining those two together, we are going to keep the sill and the axis. Okay, so they're trying to trick you here. If you put together a plus 225 and a plus 175, you're getting a 4. They did give you the 4 sphere, but remember that you are always going to keep the axis and the cylinder power, so it is going to be C. Okay, so pretty easy one there. Another pretty straightforward one is coming up. I think one of the first things that we did in the class is talk about knowing your millimeter, centimeter, meter conversions, and that's what this question is. So they want to know how many millimeters make up 1 meter. This is something that you should really just memorize. So a meter is 100 centimeters and 1,000 millimeters. Okay, so that is going to be C is the answer there, but that's helpful because that's going to help you with focal distance conversions and Prentice's rule. All right, couple anatomy or another anatomy question here, because that is definitely something that is peppered into the test as well. This question asks, cataracts are directly related to the cornea, the crystalline lens, the choroid, or the ciliary body. Okay, so this is something you really just kind of have to know. But cataracts are a cloudiness in the lens. Okay, so in the lens inside your eye, that we talk a lot about that in relation to accommodation and that lens squeezing. It also becomes cloudy when people get cataracts. Pretty much everyone gets cataracts. Not every single person, but most people do. And basically, inside that sac, that lens sac, it gets really cloudy. When they do cataract surgery, they actually take that whole lens out, and then they put in a fake lens. So, an IOL is what that's called, an intraocular lens. But that, as I've said, lens a million times, it's going to be B. Okay, so that one definitely very applicable to your everyday. Good one to know. All right. Next thing, this is a memory one. So question is, the primary ingredients in ophthalmic glass are sand, soda, lime, sand, lime, calcium, sand, lime, phosphates, sand, soda, and iron. Okay. So that is going to be B, right? So I suppose if you knew a lot about minerals, you might know that. I do not, but in this case, I would memorize sand, lime, calcium. Okay. One thing that doesn't necessarily make sense in this is like you could probably be like, all right, it's not going to be like iron, because you know that iron is pretty red. Doesn't make a ton of sense that it would be in like a clear clear glass, right? But that is definitely, I'll put in the little tidbit that was from our book on that. They do like to ask a good amount about like glass, even though it's really something that's very rarely used in optical at this point. But this tells you what what is in there. Okay, let's go on. This is a very good one to know. I think people should know this one. Fairly early in optical, it just makes things more understandable. So it says a myopic eye is essentially too long, short, aspheric, or need more information. Um, so basically, a myopic eye is too long. Okay, a hyperopic eye is too short. So you could think about like myopes, it's a bad eye, but are kind of having more of, in this case, a bean-shaped eye, and as hyperopes, kind of having like more of like a squished eye. Okay, so I'll just put an M and H, but those are good things to know. And that's why when the light rays come into the eye, or one of the reasons why when the light rays are coming into the eye for a myope, they are not able to fully reach the back, like to the retina, whereas for a hyperope, they actually go beyond. And I think like that's clear when you can see, oh, a hyperopic eye is short and a myopic eye is long, right? Okay. Let's talk a little bit about frame measurements because there is a good amount about frame stuff in here. This one's pretty straightforward. Okay. If a frame measurement has measurements of 56, 18, 135, and the patient has a PD of 68, what is the decentration? Okay, so one thing that you will definitely need to know is frame PD is the A measurement plus the DBL. So uh, DBL stands for distance between lenses. You could also say the bridge. Okay. So basically what we have here is we would add the 56 plus the 18. In that case, we're going to be getting a 74 when we put those together. Oops. So we have 74. And then we want to figure out, okay, his PD or this person's PD is 68. So we're going to do 74 minus 68 to figure out the decentration. So that's going to come out to be 6 millimeters of decentration. And in this case, oftentimes the thing that you need to watch out for here is that sometimes with these questions, they're going to try to trick you and they'll make it confusing by having it be binocular decentration or monocular decentration. In this case, this is binocular. They're not splitting it up. Like if you see numbers, obviously, like in the 30s, it's usually going to be, just one eye monocular. But in this case, they're really not doing that. They are trying to confuse you though by making it like a 12, but basically what this means is he or she is decentered 6 millimeters, with binocular decentration. Okay, with both eyes, they're somehow decentered 6 millimeters. Okay, and then they want to know, we have our 6, they want to know, is it going to be in or is it going to be out? Okay, well, our frame PD is 74, so that's larger than that 68. So we know that when they're fit, they're going to be decentered in. Okay, it's going to be, that their eyes are closer to the bridge part, the nasal part of the frame. Okay, so in this case, it's going to be A6 in. Oops. All right, so next, I believe we have another frame question, with frame PD question. Let's do that one. Oh, we have a good Prentice's rule question. Let's do that. So question is, if a -7 diopter lens is decentered 5 millimeters, how much prism will this create? All right, so what we need to know is Prentice's rule. Okay, so this is super, super, super important that you're comfortable with Prentice's rule. And Prentice's rule is power, and I should say in diopters, okay, times the decentration in millimeters divided by 10, okay? So that is a very, very important formula that will definitely come up. So you want to be comfortable with that. And so our power is -7, and we're going to multiply that by the amount of decentration, which is 5 millimeters. So we're going to do 5 millimeters. I'll put the mm in, and then we're going to divide that. So we know that 7 times 5 is 35, and we're going to divide that by 10. So the answer is going to be 3.5. Okay. All right. So one thing to think about here is this is just one lens. Okay. They're not asking you, what is the total prism induced in both eyes? They're just giving you one single lens to worry about here, right? So I think they're trying to make it a little bit confusing by putting in like 0.7 because you might be like, oh, 3.5 and 3.5. But in this case, it's C. Pretty straightforward, just using Prentice's rule. And we will have a couple more where we'll do that too, because again, this is a really big one on the exam. All right, let me show you another one. Okay, so similar. If a -10 lens is mistakenly decentered 5 millimeters, how much prism is created and what is the base direction? Okay. So again, we need to just remind ourselves, kind of like what we did earlier, what does the shape of a minus lens look like? Um, minus lenses have their apexes in the center. They look like this. Okay. And we are going to be, they also, obviously, if we were doing this vertically, would be like this. We're not doing this vertically because, well, that's a good question. They don't really say like, I don't know. Oh, they say in. They say in. Sorry, I was thinking that there was no in. So they're saying in or out, that's going to be horizontally. They would say up or down if it was going to be vertically. Okay, so we know that it's a minus lens. We need to know to first do Prentice's rule. Okay, so let's go ahead and do that. And then I like to draw out the eye to figure out the last part. So we're going to do -10 diopters, and we're going to multiply that by the amount of decentration. So I'm just doing Prentice's rule again. So we're doing -10 times 5 millimeters, and obviously that's going to be 50. And then we're going to divide that by 10, and we're going to get a 5. Okay, so we have 5 diopters. Is the prism that's induced, which is, wow, that's a lot. And we're going to think about, okay, this is decentered in. All right, so what I'm going to go ahead and do for my, just because I like to do this, we're going to put the nose over here. We know that in an ideal world, it would be here where the apex or both apexes of the minus lens would be. But because we got decentered 5 millimeters in, we're going to put the apexes over here. Okay. So if we're like, all right, where is this person actually looking through? This is their pupil. This is the direction of the base over here. So here's their nose over here. This is base out. Okay. So our long answer on this one, let's find it, would be B5 diopters base out. All right. So I don't think Prentice's rule is that hard. Like it's a fairly simple formula. I feel like it's easy to maybe mess up on this. That's why I like to draw it out. But that's how you would do it. All right, let's do another base one just to really cover this. Okay. Oh, hold on. Sorry, there's another apprentices rule one. I think it's worth doing it just to be safe. Okay. Okay. If a lens is decentered up, all right, so now we have an up-down one, 5 millimeters, and creates 2.5 diopters of base down prism, what is the power of the lens? Okay, so we need to be like, first we need to kind of, in my mind, draw this out. So let's make our eye here. And then let's figure out, okay, ideally, now we know now that we're going to be moving up and down. So I'm going to make my green line of, where the bases should actually be there. Okay. So we know that it is decentered up 5 millimeters. So it's going to be that even though its base or apex should have been on the green, but in fact, its base or apex is going to be on the yellow. Okay. So we have to be like, all right, so we know that it's up here. How can we get it to be base down prism? Okay. So let's figure out, is it going to need to be a plus lens or a minus lens? So let's just do a couple quick examples here. Maybe I'll make it nice and light. But let's try first. Let's say that it is going to be, and I don't know if there's an undo function, so I'm actually going to draw it over here just to avoid too much confusion. But let's imagine, oh, you can't even see that. Never mind. Let's imagine that we're like, okay, how do we get base down, right? So let's draw a plus lens over here. So a plus lens would be like this. Okay, so in this case, I didn't want to draw it over here because I don't know how to undo. But basically, this would mean that the pupil would be here, and this is very clearly base up that they'd be looking through. Okay, so it's not a plus lens. We can rule that out. It's going to be a minus lens that they're looking through. Okay, so they're looking through this. There's the rest of the minus lens up here. Here's their pupil. The base is clearly down. Okay. So we know that the reason we did that is because we wanted to know, is this going to be plus or minus? So we know that this is going to be a minus lens. So we know that it's either going to be minus 10 or minus 5 because those are the only minus options. Okay. But what we can do is we can do Prentice's rule backwards to figure out what the power would be. So we know that we ended with a 2.5 or a 250. So what we can do is the last step of Prentice's rule is to divide by 10. So what we can do is we can do 250 times 10, right? So that's going to come out to be a 25. And then what we can do is the first part of Prentice's rule is to multiply by the power by the decentration, right? So what we can do is we can be like, all right, the decentration was 5. So since we're working backwards, we're going to be like, okay, it's going to be 25 divided by 5 because we would have been multiplying by that 5 first. So that means that we had started, if we had been working in our usual way, we would have started with a minus 5. Okay, so I didn't write out Prentice's rule again, but I started here. I was like, okay, normally we would be dividing by 10. We're going to multiply by 10. Then I got that number and I was like, okay, normally we would have been multiplying by decentration, but basically I knew what this n number was, so I divided by decentration instead, because I knew the decentration, and my end result was the power. Okay, so that's how we arrived at that. Again, I don't know that you would see that, but it's good to have that example in case. Okay. Um, let's get to an easier question. The next one, definitely something you should know. Again, just a little bit of memory for this next one. It asks you, oh, and I should probably type in what this answer was above. The answer was A in this case for that one. Okay, the next question is, a prism will deviate light toward its base, apex, center, or normal. So you should know that the prism will always deviate light towards its base. Okay, so just an important one for you to memorize. All right, another anatomy question coming up. Okay, it is the fluid that fills the anterior and posterior chamber of the eye is A, the vitreous, B, the plasma, C, the aqueous, or D, the anterior and posterior chambers have different fluid. Okay. I definitely had to look this up. But you do want to be familiar with the different chambers of the eye. I have a picture that I'm going to put up in a second, but this is from our reading um, that we did early on, talks about the aqueous humor, and it says the clear watery fluid that fills the anterior and posterior chambers within the front part of the eye. Okay, so basically it's going to be C, the aqueous, and let me just show you. Whoops. A picture of the eye to hopefully further illustrate that. But you might be wondering, what are the anterior and posterior chambers? Okay, so it shows you the aqueous humor in the anterior. Remember, anterior means front, posterior means back. So the posterior chamber, I find that difficult to see. It's like a little tiny spot there. But basically the anterior chamber, much bigger up here. Posterior is back here, and it's the aqueous humor, is in both of those. Okay. Other ones. One thing that this reminds me of is I don't think that we had that this test has any questions about the rods and cones. So that would be a good thing to just review too before the test is the rods and cones and peripheral versus central vision. But this one asks, completely dark adapted vision is referred to as scotopic, midriatic, or myotic. Okay, so the thing that I would say here is, and I honestly don't know if this was in our readings, but it was in the test, so I figure we should talk about it. Think about dilation glasses. Those are called midriatic glasses. So we have, in offices we'll have, like, sometimes, like, people don't usually ask for them, but they're like the big, sometimes there'll be like a roll of black, like, kind of like plastic that you can, like, kind of unroll and put on, or it'll be like cardboard glasses. But those are called midriatic glasses. So it's a good way to remember this, that when you're dilated, you are completely dark adapted, right? Your pupils are really big. And so if you go out in the sunlight, it's kind of painful for if you're dilated for a while, but until your eyes adjust. So the answer in this case is midriatic. So it's C. All right, so going into some more stuff related to frames. They're talking about safety frames next. So remember that there are safety frames with two types of impact resistance, and then there's also dress eyewear, which is kind of the everyday eyewear. Okay, the dress eyewear drop ball test uses a 5/8" steel ball dropped from a height of 25, 50, 75, or 100. This is very, very likely to be on the test. So there are two types of impact resistant tests. One of them is where they actually shoot the steel ball at the lens at high speed. The other one is a drop ball test where they drop the ball. The ball is always dropped at 50 inches. So you want to remember that one distance. Again, something you just need to commit to memory. So the answer here is B. It's not talking about, the high impact resistant glasses where, again, they're shooting that steel ball. There's not, to my knowledge, a particular distance that that's done at. It's really just about the speed of that ball. So in this case, they're not asking about that. They're asking about the height of the ball, and that's going to be the 50 inches. All right, let's go to another cornea question. Um, so again, you may already know this, but good one. What is the thickest layer of the cornea? So I already put up that picture of the cornea, but I'm going to put it up again. So cornea, front surface of the eye, the really painful part of your eye. Okay, so there is clearly one area that is the thickest, right? So it's going to be C, the stroma. Pretty obvious there, but again, good idea to memorize those layers. Oh, sorry, I put in D. I meant C. Okay. Oh, I did do a rods and cones one. Okay, good. I was worried that I hadn't. All right, let's do another anatomy related one. All right, rods and cones. Again, I think this one's likely to be on the test. Which photoreceptor cells are responsible for peripheral vision? Rods, cones, ganglion, or a macrine? I do not know what a ganglion and a macrine are. But the thing to remember is that the answer is A. Okay, this is hard. I feel like you just really have to remember this one because I always forget what it is. But rods are peripheral and cones are central. So I don't know how to do that. Maybe RRP and CRC. I don't know. Rods are peripheral, cones are central. So good thing to commit to memory. All right, let's do a UV question. So remember, we always talk about UV protection and how AR provides that, how different lens materials provide that. Remember that UV ultimately stands for ultraviolet. I think sometimes we lose sight of that. But the question is, what is the wavelength of ultraviolet radiation? Is it A, shorter than visible blue waves, B, longer than visible red waves, C, 580 nanometers, or D, between 380 and 720? So this is pretty hard. You really, again, the UV spectrum is something that you're going to want to know the basics of. Before we look at those numbers, I just wanted to remind you what it kind of looks like as a picture. Okay, so we have the visible light spectrum, okay, over here. We have blue light, so high energy light. We know this is dangerous too. And then we also have UV or ultraviolet, which is damaging to the eye as well, okay? So you can see here kind of the way things are progressing, right? It's shorter over here and it gets longer over here. So that's going to help us eliminate some of these. Um, it says longer than visible red waves. Well, red waves are way over here, in the visible light spectrum. So if you're seeing anything that says visible, that means that like it's going to be over here and it's going to be longer. Okay. So, the answer to this, just to tell you, is A. Okay, so it's going to be shorter than the visible blue waves. Now, remember that blue light or high energy visible light is not, I'm sorry, high energy visible light is going to be like here. It's going to be don't confuse it with blue color light, but it is longer than the UV. Okay. So basically you can see here, here's the high energy blue light that is visible, and then here's the UV. So the answer is that it's shorter than the visible blue waves. Now that doesn't give you like that that's tough. So I figured I would also have you take a look at this because this might make it a little bit simpler too. This is from our book, a part that we read a little while back, but it's a little chart that shows us the actual numbers of the spectrum. So you could see that ultraviolet is right here. It's going to start at 200 and go to about 400, right? And then the visible spectrum starts at about 400 and goes to about 750. Okay, so that's here. You could say, 400 to 750, and this is somewhere between 200 to 400. Okay, so that would help you to know like if you know, okay, UV ends around 390, you would know, okay, it's not going to be UV is not going to be 380 to 720. It's not going to be 580. Okay. So you want to memorize, where does UV start? Where does UV end? So think UV 200 to about 400, visible spectrum 400 to 750. Those are the parts that you really want to, those two categories that you really want to memorize. So I'll circle those on here um, as the um, so just two separate um, number ranges that you want to memorize. Okay. We have just a couple more questions. Let's go into transposing a prescription because we have a few minutes to just go through that. So our next question is asking us to transpose a prescription. Let me just grab, hold um, it's kind of a weird two-part question. Let me put in part two first. Okay, so this is the possible answers, the actual question. Okay, so the RX we're going to use is here. Use the below example. So we have -2, minus a half at 10, minus 150, minus 1 at 50. Okay, and it's asking us to transpose the RX. So very important thing for you to know. Definitely something that will be on the exam, something that if you are a technician, you're definitely very familiar with using on a daily basis. In optical, it's super helpful for troubleshooting RXs and looking at how much did things get tweaked or how did they get tweaked in RX checks. That's the part that, I feel like transposition comes in on a daily basis the most. Okay, so how do you transpose? You have to change the sign of the cylinder first, okay? So in this case, what would we be doing? Our cylinder is minus, so we're going to go ahead and we're going to make that a plus 50, okay? Because we're transposing um, this eye. They said OD, right? So this is the OD, this is this eye. Okay. Add the first two numbers, sphere and cylinder, together algebraically. Okay. So what we're going to do in this case is we are going to put together the sphere and the cylinder. So we're going to go ahead and do, this is going to become these two. So it's going to then become a minus 250. Okay, a minus 250 plus 50. And then what do we have to do? We have to rotate the axis of the cylinder 90 degrees. Okay, so that can get a little confusing at times just because remember that we only go from 0 to 180 with our axes. We don't go to like 190 or 210. We start again at 0 if it gets past 180. Okay, so in this case, we're not going to get past 180. So we're going to add 90 to this. So in this case, we would be at 100. So if we transpose this prescription here, we would be putting it into plus cylinder form. So if you had an RX come in from an ophthalmologist office, it would be, you know, something normally it would come in plus cylinder, so it's helpful to know what that would look like in minus cylinder. So you would be here basically. Okay, so we could see that in this case the answer is going to be C. Okay, so that's definitely something that you want to just get familiar with. Pretty simple process. So just following these 3 steps. All right, guys. So I still have a good amount of stuff. I don't have tons and tons. We're kind of getting towards the end of things, but I do wanna I do want to make sure that we go through this well. I know that we're pretty much out of time for today, so I want to let you guys go. I think I'll give you guys a heads up on it, but I think we will still have to have one more meeting. I was kind of hoping to get through this in one, but I think that ultimately it's gonna have to be one more that we do to really fully get through all of this. So I'll send you a message about that. I think we'll plan to do it in 2 weeks, but yeah, that is the story for tonight. So thank you guys, and I'll talk to y'all soon.
Yep. Have a good night.
Thank you.
Yep.
Have a good night.
Night.